Welcome to the Entangled Show, a weekly conversation where we bridge the gap between high-level physics and everyday reality. I'm your co-host, Pete Codella, streaming from Utah's Salt Lake Valley.
And I am Sumit Parashar. I'm from Bhilai and live in Lehigh. I live in two places at once, just like a quantum particle. I coined the term Quantonomy, which is what this show is all about. Thanks for joining us.
Sumit, hi, how are you?
Good morning, Pete. I'm doing fantastic. How are you?
Good. Happy to talk about our topic today of superposition and episode 2 of the Entangled Show. Before we jump in, I'll mention from listening to episode 1, we did talk about some visuals that we were sharing. If you're just listening, you're missing out because we're also recording video. You can find us on YouTube. You can see the video and our visuals if you are so inclined. Sumit's put a lot of time into some of the visuals, so I'd recommend it. We're at Entangled Show on YouTube. We also want to hear from you. We'd encourage you to email us with questions or feedback. That's info@entangled.show. And if you just go to our website, which is entangled.show, you can find and follow us on social media and engage with us there. We're monitoring those conversations and would love to hear from you. Wherever you stream your audio podcasts, we are syndicating our show, so it should be available for you there. And with that, let's talk again about our word of the day, what we want to be the word of the year in Webster's Dictionary, Quantonomy.
Thanks, Pete, for sharing all that information with our viewers. We love to interact. We love to learn from you on how we can make this even better. Thanks for that. So back to our word, a quick recap is that as is above, so is below. That is a known maxim. And so along those lines, we have astronomy as the study of celestial objects. And hence, quantonomy becomes the study of quantum objects. That's a quick definition.
We covered quanta and qualia last time. Anything you want to cover there?
Thanks for bringing that up. Somebody had a question about qualia. Let's get to that. Quick recap along those lines too is that quantonomy covers the study of quantum objects. Quantum object was the first thing we talked about last time. The singular of a quantum realm object is called the quantum object. Plural of that or multiple of that is quanta. And qualia is a relatively new concept. I'll take a second and talk about that. Our view is that quantonomy will become an umbrella field of study where we include science and also a bit of a fringe science, which is connecting consciousness to science. It's not an actual science yet, but in our opinion, it will soon be. So qualia, Qualia, is a property of a subjective experience by the consciousness. So we took an example of a drink that this time I'll switch the example to tea. Every time we drink tea, it feels slightly different. In my experience, I've never had the exact same tea over and over again. We feel that difference because it was prepared in a slightly different way. You cannot 100% replicate the recipe all the time. So maybe the sugar turned out to be a little lower in this particular tea, or the caffeine went a little bit high. So we as human beings, as conscious human beings, are very sensitive to those changes. Qualia means we are having a subjective experience of drinking that tea. And it is, in our opinion, kind of tough to quantify that experience. If we were able to quantify that experience, they would say, hey, this is 7.895% sweeter than what I had last time. So I know it's a difficult concept to explain. But one of the things that we want to do with the show is to expose all of us to these new words. And if it tickles your curiosity, we would encourage you to go and find out more about that word. And in the 20 minutes time that we have for each podcast, it is difficult for us to go deeper into a specific topic. Qualia, Qualia, is a great new subject connected to consciousness.
And again, quantonomy, we're saying, is the study and management of principles, governance, and economic architecture of quantum systems.
Absolutely. Right on the dot.
All right. So we promised we would talk about superposition. I do want to point out there's a little strategy to the three pillars of quantonomy, maybe by happenstance, maybe not. Superposition, Sumit, probability, Pete, entanglement, the entangled show. How do you like that? SPE,
Love it.
all the stars aligned. So talk to us about superposition.
I think we have picked up on a really difficult task here is that our objective is to demystify quantum phenomena or autonomy. A lot of major scientists have worked on these phenomena. They have scientifically proven that this phenomena actually does work. But it is so counterintuitive, so weird, and so spooky. And by the way, these are all official words that have been associated with quantum studies for a long time.
It sounds like Halloween, weird and spooky.
It does. You don't like my cat here?
Your cat's awesome. He looks a little stiff.
Yeah. It's because I gave it some training yesterday night on how to behave when it's on the show. But yeah, this is what the Quantonomy is all about. You will hear concepts and ideas and things that are so weird and spooky and counterintuitive that the reaction that we as humans have is that no, this is not right. And we are talking about something that is fictitious. But believe me, it's not. Having explained the concept of why we think it is spooky, counterintuitive, and weird, one thing I will add along those lines is that while growing up, we were taught a certain method or algorithm to learn science. And it was experiment, observation, inference.
The
That was
scientific
the
method.
that is the scientific method. Experiment, observation, inference. We grew up with that. That's kind of encoded in our genes. Now, with us moving into the quantum realm, all of that goes for a toss. Because what I'm going to say next is going to probably blow your mind. In the quantum realm, if you observe something, it changes its behavior. So there goes experiment, observation, inference, because now as you observe, you are messing with the actual experiment. The observation becomes a part of the experiment, not as a third layer where you are actually studying the experiment. So the word observation or measurement actually has a very different connotation when it comes to the quantonomy world.
And could that be because the observation is happening by different people? Or are you saying that the very act of observing something changes what you are observing?
Pete, you are on to something there. That, in essence, is the crux of the matter here. Think of things that we're going to study as systems. As human beings in a body, we are a system. The space right here in front of me, if I take that pocket, that's a system. This cat, it's a toy cat, but it's a system.
And all these systems will interact with each other.
Yes. So I think this is like the simplest level, but as we go to the next level, it gets complicated. Now talk about interactions between systems. So as a human, I'm interacting with you, and the mechanism we are using is the human language. Same thing, I can interact with Mr. Schrödinger's cat here. And when I touch it, there is an interaction. There is quantum particles on my skin that interact with the quantum particles on the toy. And there's a bit of interaction. I get the feedback saying this is the qualia of my experience right there.
I want to point out that our interaction is not just language, right? We've talked about superposition and this concept and what we want to do in episode 2. That was language. And we're having this conversation now, and we're using video. So there are multiple, perhaps, systems in play just for us to present and have this conversation.
Absolutely. So superposition, we were talking about interactions between systems. I am a system, our bodies are systems, and we interact with everything. So everything should be taken as a system. And the interaction between systems, when that occurs, things start to become really interesting. That was the context, but let me bring us to the topic of the day, which is superposition. Again, in my studies, in my understanding of the word superposition as a pillar of quantonomy, and the word that is being used to describe a certain phenomena. I think if we go back to the drawing boards and maybe bring in some linguists, we can explain what happens behind the scenes and then come up with a word that truly defines superposition. I have some visuals, but a simple definition of superposition is that when we are not observing the pocket of space in front of me as the waves. Now, the waves have a potential or potentiality of turning into particles given a certain condition. The condition is that if I interact with the system in front of me, which is this box, and if I observe, say, a piece of pencil in front of me, the waves then collapse into particles that becomes this pencil, and hence I have this pencil right here in front of me.
You want to show some of those visuals?
Yes. So, like I was saying, the word superposition is broken up into two words essentially. The word position is the base. Our way of describing or elaborating on superposition in all simplicity would be look at this word position. So, superposition now is many positions concurrently or at once. You have position one, position two, and position three. All of these three combinations encapsulate into one, and then we call it the superposition.
That concept reminds me of the word hero or man. And then you have superhero and Superman, which has very different connotation, right? A superhero can do amazing, incredible things. Superman is a man with endless power.
I love that analogy. Okay. Superposition can be explained in the other way. If I think of the space right here in front of me, there are waves going on in front of me that most of them are invisible to us. But if you took a cross section of the space in front of you and try to visualize what that cross section looks like, I would say let's visualize this cube right here. Within this cube are waves that we could not see on the last slide because I had blocked out the wave part of it. In this visual, we can actually see the waves occurring in that one particular unit of space. A unit of space will come up in a future section. In the last slide, we saw that there is potentiality inside that cube, there are waves inside that cube. And here, what we're observing is that when I look at a certain section of space and it's got potentiality, it shows up as a particle just because there was an act of measurement. So, in terms of the systems that we talked about, this system is corresponding or interacting with this system. And as soon as there was interaction, the wave collapsed into a particle. And that particle was then brought into our physical world. So above the world of quantonomy. And that's how we can actually see the particle.
So, for those who aren't watching the YouTube video, this is going back to the example you shared earlier with the pencil. In the one system, with the eye of the observer is looking into the other system. And when that happens, the wave is a particle at that moment of observation.
Thank you. And I keep forgetting that we have audience that would not be viewing. So now I'm going to go back to the last visual we saw and bring up the reason why we are talking about these three different phases. This is the fundamental cube of space right here in front of me, and these are the waves within. But then the concept of superposition says that the particle exists in position one and position two and position three before you have observed it. The act of observation mandates the wave to collapse into one, but before you made the observation, it was in all three states together concurrently. And I would use the word and for position one and position two and position three. So that's superposition for you.
So, Sumit, can we say that the superposition is just a point in time, an observation of a freezing of things for a millisecond to look at it and you record what you experienced there, but that doesn't mean that before that observation, it wasn't in multiple states. Is that the idea?
Yes, you are looking at a certain particle in a certain state, and the state has properties, which is that when time flows at one specific instance in time, you saw the particle, you interacted with it, and hence it became a particle. There's one more aspect to it is that there are coordinates or position of that state attached to it. So the state of the particle has the position. The position is x, y, and z coordinate plus the instance of time when you saw it.
Before you talk more about Schrodinger's cat theory, can I share some examples and you tell me if it's superposition or not?
Absolutely.
So this goes back to our conversation in episode 1, like on or off, yes or no, being awake or asleep. Is that an example of superposition?
From an external observer's point of view, who is outside the home, yes, that you are in a state of superposition. So I'm outside your home and the home is a box. You are in the home and you could be in multiple states. You could be sleeping and awake. And as an outside observer, I would not know. At the moment I call you, wait, I need help with this. That's when I break the superposition and we are mandated to choose a certain state.
How about my favorite sports team winning or losing a game?
I will take you to the next step, and in the next episode, we'll read all of that. Well, now we're talking about probability.
How about defining something as black or white?
That would not be superposition. So you are choosing an option. English implies you are choosing a certain option. So if you had a piece of paper in a box and we did not know the state of that before we were packing the box, it is in a superposition whether it is black and white. But the moment we open the box and observe what's inside, it is forced to make a decision of black or white. And then it manifests itself as a color. What the other black or white is not technically in superposition. If you bring in the observed, yes, that is superposition.
One final thought is, what about a higher power or God who the scriptures say can see beginning from end? I mean, to me, that feels like our experience is all superposition, and depending on when it's observed, it's frozen in time. I don't know if that concept fits or not.
So, Pete, that's a really high level thought. And I think one of the episodes will pick that up.
Bring in a guest who can help us sort that out.
Yes. God as an entity, it'll be difficult for me to address, but definitely a deep topic.
Okay, we'll talk more about it.
All right. Wrapping up the discussion on superposition, I actually want to give you an explanation of why we have this cat right here. If you had one key takeaway from this session, I would say remember the cat. The cat was an example that was brought up by Erwin Schrödinger, who was a leading quantum scientist.
This
Who
thought
did-
experiment goes back to written correspondence between Schrödinger and Einstein, correct? 1935.
Yes. So that was a point in time where there was a lot of debate between major scientists like Albert Einstein on one side and Niels Bohr on the other side. And this idea of superposition is so absurd that Albert Einstein refused to believe it. We are mere mortals in terms of IQ, in terms of our understanding, in terms of vision. We are not even close to any of those gentlemen. But to prove the absurdity of superposition, Schrödinger created this thought experiment saying if you have a cat and you put it in a box and create a situation where it could live or die, he came up with a thought experiment with a mechanism that would release a nuclear element in the box, but that would be triggered in a certain condition. What happens to the cat after the box is sealed is not determined. It takes place after the box is sealed.
It's a
So
question mark. For us, what's happening inside that box, we don't know. Either can be dead, can be alive. The state is both because we don't know the answer.
Pete, you pretty much summed up. That's exactly what I wanted to say too. In the box, the cat is dead and alive, and we will only know the actual outcome of that experiment when we observe or when we open the box, actually take a look at it. And at that point of time, we know Schrödinger came up with this example in absurdity to prove that this is so weird. Things have a way to happen or occur by themselves. This experiment became so famous. I don't think Schrödinger actually intended this experiment to be as famous as it is. When we think of superposition, the easiest way to remember is this: put a cat in a box. When you open it, you don't know if it's sleepy, dead, or alive.
Some of the
Take a
cat
quick
you chose looks creepy and weird. And I'm going to bring it all together and just say for Halloween, you should dress up like that creepy, weird cat.
Thank you. I know what I'll be doing this Halloween now. These things are tough to understand. My quick recap on superposition is, in a way, did not make any sense in this episode. Your key takeaway should be is that there is a cat that can be dead and alive when we are not looking at it, and it chooses one of the options when you are looking at it. So it can be at multiple states at once. The famous thought experiment has been attributed to Erwin Schrödinger, and we thank him for all the work he has done. There's a lot more, even in terms of mathematics, in terms of prediction of what a particle can do. He wrote a famous Schrödinger equation that has worked wonders for us. So my salute and our respect to Mr. Schrödinger.
Okay, that's superposition. Next time we'll talk some more about probability. Good to talk to you, Sumit.
Thanks, T. We'll talk soon.
The Entangled Show podcast is available on YouTube and wherever you get your podcasts. Please like and subscribe to the pod. Connect with us at entangled.show or send an email to info@entangled.show. I'm Pete Codella. Thanks for listening.
I am Sumit Parashar. Signing off for now. Thanks again for joining us here at the Entangled Show. We'll see you next time.